All right. Hi, everyone. Welcome to MLFL this week. And this week, we're really honored to have Dr. Dimitris Tsipras from Stanford University as our speaker. Dr. Dimitris Tsipras is a postdoctoral scholar at Stanford University, advised by Persian Liang and Greg Valiant. He obtained his PhD from MIT, advised by Alexander Madry. His research is aimed towards understanding and improving the modern machine learning toolkit, focusing on topics such as reliability, benchmarks, and interpretability. Now, without further ado, let's welcome Dr. Tsipras.
Hello, everyone. Thank you for the introduction. So today I wanted to talk about a few representative works in this general direction of how can we get a better sense of how our machine learning models work by trying to better understand their successes and failures in different scenarios. And of course, I'm sure you're all seeing the news that deep learning is being really transformative these days. And every time I make this slide over the last 5 years, the argument becomes easier and easier, starting from things like emergent classification, which really showed the potential, to things like having deep learning models learn strategic games, scientific discovery with protein folding, learning to generate language, learning to generate code, or this really impressive text to image generation. Things are really going. And all of these developments are really exciting. There's actual genuine progress happening here. There are many useful tasks that we were not able to do before and are able to do with today's machine learning technology. And interestingly, the recipe behind all of these advancements is quite simple and common. Basically says, get all the data you can get your hands on by just aggressively scraping the internet, be it archive, Flickr, Reddit, Wikipedia, anything you can get your hands on, and then train a really big model, the biggest model you can using that data, and then potentially apply this model downstream. And within simplicity, this is actually a very powerful recipe. Like we have models now that are able to do many different tasks without having humans to supervise them in a very fine-grained level. And in general, the whole idea is that instead of trying to teach your model how to do something specific, you're just teaching it how to model the data that it sees in the wild, and good things happen. At the same time, things don't always go the way you would expect. Like the outcome of this process is not always predictable. And this can have both good and bad manifestations. So the bad is that models often fail in ways that you didn't really expect them. For instance, if you try to optimize this half cheetah to run as fast as it can, it gets into this weird optimum where it will flip upside down and start jumping around in order to run. You have things like self-driving cars that for some random reason tend to go towards barriers. So even when these systems work most of the times, there are edge cases where they fail in ways that you wouldn't expect them. Or this recent example from the Anthropic paper where a chatting bot is very happy to explain to you that one of the good ways to get into selling cocaine is to raid an existing drug dealer. At the same time, it's not all bad. And perhaps one of the most prototypical examples here is this phenomenon of adversarial examples, where models that are normally highly accurate can be fooled by a tiny amount of noise. These are called adversarial examples, and starting from a classifier that correctly classifies this pig, adding a tiny amount of adversarial noise causes this classifier to classify the image as an airplane. Okay, at the same time, it's not all bad. Like sometimes training these large models allows them to succeed in ways that we didn't expect them before. For instance, there's this phenomenon of in-context learning where large language models trained to model internet text are able to learn by just a few input-output examples that we provide them. For instance, if I give the model a few examples of English to German word translations, the model is figuring out that I'm actually trying to do English to German translation and will happily provide new translations, or similarly with addition. And this was one of the primitives that allows the models to succeed in many tasks without fine-tuning. Or a phenomenon like this chain of thought reasoning that says that, oh, if I prompt my model in order to encourage it to show its internal thought process in some sense, then it can get better at certain reasoning tasks. Or if you want, you can even skip this, and if you just prepend, let's think step by step in the answer of a model, then it turns out that it becomes much better at reasoning about these sort of simple, first grade arithmetics. So our goal for today's talk is to dig a little bit deeper into some of these surprises, the good and the bad. And the hope here is that by looking at how models behave in these unexpected ways, we can get a better sense of the way they work internally. Because if all you're looking is what the accuracy of the model is on the task it's expected to perform, then you're not really going to see many things. The model is either going to be correct or it's going to be wrong. But by probing its behavior on behaviors that we find surprising, we can actually get a better sense of what's going on. And this talk is going to have two parts. So first, we're going to talk about adversarial examples, and then we're going to talk about in-context learning. Okay, so let's get started. So the first question when you see adversarial examples, and just to preface, this is joint work that I did with mostly my collaborators back at MIT, most of them were grad students at the time. And what is really intriguing about adversarial examples is that they don't really make sense at first glance. You see this example and you say that, oh, I have a model that correctly classifies a dog as a dog, but the moment I add this imperceptible noise, the image doesn't really change, but suddenly the model is completely confused. So what is confusing is, okay, why is this specific perturbation important? Clearly, we as humans know what dog is. We can see that this worst case perturbation has nothing to do with the dog, but somehow the model is very sensitive to this perturbation. And I want to take a moment and pause and think a little bit that this is actually a very human phenomenon. Our surprise to the effect that the model is confused by this specific perturbation is actually deeply rooted in the fact that we as humans do not view this perturbation as meaningful. So can we dig this thought a little bit deeper? So one natural hypothesis here for someone seeing adversarial examples for the first time is to assume that, okay, the model is really accurate and it has some adversarial examples. So in some sense, the model is making its correct and accurate predictions according to mostly correct features. It's paying attention to roughly the right things. But there are these weird vulnerabilities and these weird brittlenesses that, well, if you try hard enough, you can make the model misclassify things. So to put this in a cartoon drawing, you can think of linear classification when you have some green features and some blue features. And the green features are the useful features. These are features that are useful for classifying these images. And then you have some blue features that are useless. And they don't really convey semantic information, but somehow the model is sensitive to them. And these are the features that the adversary manipulates. So this cartoon drawing is meant to illustrate this fairly natural viewpoint that says adversarial examples are just bugs. The models are working fine, but there are some weird edge cases that can cause them to fail. But can we actually test this hypothesis? Can we get a sense of whether this is the case or not? And for this, we can design a simple experiment that goes as follows. Starting from a data set of cats and dogs, we have a very simple classification task. Given an image, can you tell if it's a cat or a dog? We have a data set comprising of a bunch of dogs and a bunch of cats. And now we're going to transform this data set by creating an adversarial example of each image towards the other class. So we're going to perturb the image of the dog to make the classifier predict cat, and we're going to perturb all images of cat to make the classifier predict dog. And all of this is for a fixed classifier. You train your classifier first, and then you create these adversarial examples. Now, for the next step, we're going to actually relabel these images based on the label predicted by the classifier. So now we're labeling this perturbed dog as a cat, even though to our eyes, this is mislabeled. This clearly looks like a dog's tail. And then we're going to train a new classifier from scratch on this mislabeled dataset. Finally, we're going to test this classifier on the original test set. So just to quickly reiterate, starting from a normal dataset of cats versus dogs, given a fixed machine learning classifier, we're going to perturb these images towards the other class. So now every dog is predicted as cat and every cat is predicted as dog. And then we're going to label these images according to the predicted label. Train a model from scratch and test it on the original test set. So how well do we expect this model to do? Well, at first glance, the training set is completely mislabeled with respect to the test set. We're training a model on things that look to us like a dog but are labeled like a cat. And then on the test set, we're going to test a model on dogs that look like dogs and are labeled as dogs. But, well, it turns out that the model is actually able to do pretty well. For instance, on the CIFAR-10 task of cats versus dogs, it's able to get 78% accuracy. And similar results for ImageNet or the full CIFAR-10. So this gives us a bit of a pause, like what is happening here? How is the model able to generalize by being trained on this completely mislabeled data set, but somehow there's enough information to generalize the original test set? So clearly our mental model for adversarial examples is missing something, right? Like if adversarial examples were just bugs and they were just perturbing meaningless features, then there's no way that they would carry this semantic information that allows us to train a new classifier to generalize the test set. So instead, one way to think about it that actually makes sense and to reconcile these behaviors is what we can call the robust features model. So instead of thinking of features as useful and useless, you can think of useful features as belonging into two groups, that being robust. These could be things that are actually hard to change by small L2 perturbations. So these could be things like what we perceive as a car wheel or a face or the background of a dog. And then there are non-robust features that could correspond to faint patterns or small idiosyncrasies that the model is paying attention to. And the key idea here is that both of these families of features are actually useful. So both of them carry semantic meaning towards making a correct prediction. It's just that one of these families of features is robust and the other one is not. And from this perspective, actually, the experiment we just presented makes sense. All the accuracy of the model is actually coming from non-robust features, because we're starting from some data set where our dog images have normal dog robust features and dog non-robust features. And then we're adding small perturbations to turn these images into something of a different class. So we're effectively flipping the non-robust features. So now we're creating images where the robust features stay roughly the same. The non-robust features change towards features of the other class. And this is exactly what the model is able to leverage, because these images will have non-robust features that point to the other class. These images will be labeled with the other class. So the model is able to use these non-robust features to generalize the test set. And sort of by the design of this experiment, all the model accuracy is coming from these non-robust features. So to summarize, what does this imply? Well, this experiment shows that non-robust features can actually be predictive. You can take a data set and you can make very small changes to this image and produce features that generalize the test set. So this clearly tells you that there is signal in non-robust features that allows you to generalize to the test set. And since we train our models to maximize accuracy, they will utilize any feature that is useful. There's no distinction between robust and non-robust. So if you put one together, you can see that, well, the vulnerability of a model to adversarial examples can actually, to some extent, be explained by the presence of non-robust features in the data. There are some faint patterns in the data that are not really salient to us, but if we train our model, the model will take advantage of these patterns, be more accurate, and thus be brittle. And moreover, there are two other interesting implications that come up with the phenomenon of adversarial examples. And one is this really interesting phenomenon of transferability. So what this robust features model says is that if you create adversarial examples for one model and you apply them to another model, these are likely to transfer. So different models are likely to be confused in the same way. And this is actually something that is true in practice. It was perhaps one of the reasons why adversarial examples seem quite fundamental. Like they're not something that just applies to one model, but it can transfer to other models trained on the same data set. And it's actually something that's explained by this robust features model. If adversarial examples are coming from the models being sensitive on non-robust features, well, since the same data set has the same non-robust features, if you train two models on it, they're likely to rely on these features in a similar way. So this means that if you create adversarial examples by perturbing the features that one model relies on, this will also fool the other model because the other model is also relying on the same features. And secondly, there seems to be this trade-off between robustness and accuracy. So in some sense, if you want robustness, then this would mean that your model has to only rely on the robust features. But if you want accuracy, then taking into account the non-robust features is actually quite useful. And it turns out that this is also something that manifests in practice. And it turns out that models that tend to be more adversarially robust are also typically less accurate. And there are some nuances of this that I'd be happy to talk about, but the first order approximation is that these things can be at odds for a fixed data set. And perhaps this seems a bit peculiar, like talking about non-robust features, but it's not really something that's very strange. In fact, there's a lot of work by now that shows that models can actually rely on features that we don't really think make a lot of sense. For instance, it could rely on linear direction, pay a lot of attention to texture over shape, rely on high frequency components or dense feature mixtures. And the key takeaway is that all of these different features, even if they are not entirely intuitive, they are actually valid from an accuracy perspective. If you're training your model to maximize accuracy, even if there's some weird feature that we as humans would not pay attention to, the model has every incentive to learn it and improve its test accuracy. Because to discuss these features do generalize. Okay, so one natural question is, okay, what would happen if we try to make our models robust to adversarial examples? Is something like that possible? Well, the first thing to say is that, okay, of course, we need to change the way we train our models. In some sense, we never asked for our models to be robust, so it should be no surprise that they actually don't. So the way we train our models in the standard way, standard generalization, says that I want to train my model to minimize the expected loss over random XY pairs from my distribution. So here theta corresponds to the model parameters, and you sample random XY pairs from a distribution, and you want the loss to be low on average. But now, if you care about robust machine learning and specifically adversarially robust generalization, then you need to modify this objective. And you need to say that I don't just care about having a low loss on an individual point, but I also want to have a low loss on all the small perturbations around that point. So if I also introduce a perturbation delta to X, and I choose the worst case perturbation by maximizing the loss over some small neighborhood, then here I'm directly encoding robustness into this training objective. So in other words, I'm being explicit about the set of invariances that I want my model to satisfy. And if we frame the problem like this, well, then optimizing this min-max loss corresponds to an instance of robust optimization. And in order to solve it in practice, you can think of the min and the max as corresponding at two different things intuitively. The inner max corresponds to finding a worst case perturbation. So you can think of all the standard methods for finding adversarial examples, that is, examples that maximize the loss of the model, exactly as trying to solve this inner maximum. And you can do this, for instance, with just projected gradient descent. Just move locally in a direction that maximizes the loss without stepping out of the capital delta. And then the outer minimization problem corresponds to learning a robust model. It corresponds to saying, I want to find parameters theta so that the loss is low, no matter the delta that the adversary chooses. And in order to do this, well, we train our models normally using stochastic gradient descent. And here it's a little bit tricky because you're trying to optimize a maximum instead of optimizing an actual differentiable function. But it turns out, and I'm happy to discuss more offline, that all you need to do here to actually reduce the value of that max is train on worst case inputs. So instead of just picking a random XY pair and training on it, you take this XY pair, you compute a worst case attack, and then you train to minimize the loss of that attack. And this is also known as adversarial training from Goodfellow et al. And it turns out that actually leads to robust models. The one caveat that you really need to be careful about is making sure you have reliable attacks. So this means that the worst case inputs that you're training your model on have to be sort of worst case in some sense. And a lot of the failures of early attempts to build robust models came exactly from this gotcha where you're training your model to be robust against some attacks that you can find. But if your attack consistently misses adversarial examples, specific adversarial examples, then your model doesn't become robust in general. And overall, once you take care of this, then it turns out that you can actually get models that are reasonably robust. For instance, on ImageNet for a bunch of different perturbations, L infinity, L2, translations and rotations, you can actually get meaningful robust accuracies. And what robust accuracy means is what fraction of the test set can the model classify correctly, even under the worst case perturbation. So even if I give my model and the test set to an adversary, and I tell the adversary, make these examples as hard as you can, then the model still predicts correctly, again, within the specific L2 or L infinity norms that we have. And now going back to this question of like, okay, if adversarial examples come from the presence of non-robust features, are robust models somehow relying on different features of the data? And this is a bit of a longer discussion that I cannot get into too much depth, but I want to show this like nice visualization that says, here we're going to take a standard model and transform this primate into a bird. So I'm creating a large adversarial example where I'm trying to make the model really confident that this is a bird. And if you missed it, you probably missed the transformation that happened. Nothing really changes too much. The texture of the primate is changing a little bit. But if you do the same thing for a robust model, then you actually see changes much more salient. And here we're not doing anything weird. All we're doing here is just taking the original picture and doing gradient descent to maximize the probability of predicting bird. And we see that to some extent the model is indeed sensitive to actually quite different features because this local search for adversarial examples led us to something that looks to some extent like a bird. And yeah, and like one interesting thing, like I like this visualization on one hand because it does show us that robust models are sensitive to different things, but it also makes robust models this really nice primitive for doing a bunch of image synthesis tasks. So if you have this primitive that says maximize the probability of another class, and then features of that class pop up, you can do things like image generation, translating horses to zebras, super resolution, and things like in painting. Yeah. So to summarize, one of the key takeaways from this first part are that adversarial examples can actually be attributed to some extent to the presence of non-robust features in the data. Our data has predictive patterns that our models learn, but these patterns are not robust and thus fool the model during deployment. And it turns out that if you actually train on worst case perturbations, you can actually make your model robust to these worst case perturbations. And these robust models tend to actually rely on different sets of features. Okay, so moving forward into part 2, and this is joint work that at Stanford with Shivam and Percy and Greg, we're going to talk about in-context learning. So as I briefly mentioned before, this is this phenomenon that we see in large language models, where we train these models on a lot of text from the internet, and these models are actually able to produce quite coherent text. You can prompt them in some way, and they're actually able to produce text. But one of the happy accidents is this notion of in-context learning, where if I start, for instance, if I want to make my model translate from English to German, I can just provide a set of examples, and the model is able to figure it out afterwards. And you can actually do more interesting things. You can say, oh, I want to classify movie reviews into red or green, and the model sort of figures out that red is negative, green is positive. Or things like, oh, I want to do addition, but instead of having the plus sign, I'm going to use the pound sign. And again, the model is actually able to figure out that from a few examples that this is what you actually are trying to do, and autocomplete in the right way. And this is really interesting because all of this is happening purely at inference time. And this is one of these primitives that allowed models to really perform well on tasks that they were not trained explicitly on. So these models are just trained on the web. You just train them to predict and model the text that is found on the internet. And somehow we're able to apply them directly on tasks like sentiment analysis, summarization, question answering, without fine-tuning them, just because we're able to specify through examples the input-output form that we care about from these tasks. And now one interesting question is, are these models really learning new tasks? Like, are these tasks that we're seeing actually new tasks that they're learning from these in-context examples, or are they just tasks that they've seen during training? And if we focus on the English to German translation case, well, the model has obviously seen English and German translations. So in some sense, the task of translation is not something that you learn from this data, but the model did have an idea of what book corresponds to in German. And even the notion of like translations between languages happening in a list is also something that you find on the internet. So to some extent, maybe one can ask, okay, the model is not really learning something new here, but maybe just retrieving the task that is saw during training and predicting according to that task. But the problem, like when you train on such large corpora, is that you have no idea how to reason about the training data. How can I even go and say, okay, what are the examples that influence this behavior, and try to see if this task was in my training data or not? So in order to circumvent this, I wanted to focus on a bit more of a clean setting, where we ask in a very abstract sense, what can transformers learn in context? And specifically, we're going to study simple function classes that we understand well in a synthetic setting, so that we don't have to deal with all these questions about, oh, was this in the training data or was it not? Okay, and specifically, the primitive that we're going to care about is the question, can a model in context learn a function? So what this means is you start with some function, let's say from RD to R, and then you have a model. And if you sample a bunch of random points x from the domain of this function, xi through xk, x1 through xk, let's say from a standard univariate Gaussian, then you compute the value of f on these points. you feed this into the model, and then you sample a new query point and you feed it into the model. And we're asking, can the model predict a y that approximates f of x query? So just to reiterate, because this is at the center of our setting, what this says is that if a model can in context learn a function, then it means that given input-output examples from that function, x comma y pairs, where x is x and f of x is y, then the model is able to approximate this function on a new input. Now, we can take this one step further and say, what does it mean for a model to be able to, and we're going to refer to this set of examples and queries as the prompt. And now we can take this one step further and ask, okay, can the model in context learn a function class? So what this says is that, okay, if I have a function class of functions, let's say linear functions, then I sample one function from there at random, then I sample the x's, and then I ask my model to predict the value of that function on a new x. If the model can do that, then we say that the model can learn the function class f in context. And notice this is just a property of the model. So I can actually test this quite easily. Given a fixed model, I have my function class f. I can sample a bunch of random functions, sample input-output examples for these functions, and ask, can my model approximate a random function from that class? And everything here is actually happening for a fixed model. So this is in some sense inference time. There's no training going on here for now. Now, how would I go ahead and train such a model? Where we're going to use transformers. And the way we're going to train them is by just directly training them to learn this function class. So this says I'm going to sample a random function f from this class. I'm going to sample a random prompt from this class. And then I'm going to teach my model how to predict the right y at every single point of the sequence. And based on the architecture of the transformer, what you end up getting in the end is that y1 will only depend on x1, whereas y2 and so on will depend on all the previous input-output pairs and the corresponding x. So for instance, yk depends on x1, f of x1, x2, f of x2, up until xk, but of course not on f of xk. So this is exactly how we're going to train the model, and we're going to do sample a random f, train the model to predict better on this f, and then rinse and repeat by sampling a new function f and teaching the model again to approximately in context learn this f based on a set of random prompts. And just to clarify here, there's no pre-training or training on text. This is the whole process. We're doing this from scratch. We randomly initialize the model and we train it to be able to in context learn functions from this family. Okay, now you may ask, can we train a model that can learn linear functions in context? This is perhaps the simplest family of functions you can come up with. And here we're going to work with 20 dimensions. So these are 20-dimensional linear functions, which depending on your point of view can be either low dimensional or high dimensional. Like in general, I would say that these are high dimensional functions. Like they have a lot of the probability of landing on any specific orthon, for instance, is really low. And in general, things like nearest neighbors do not tend to work that well. So here we're going to train the model as we already talked about, and we're going to look at plots of this form. So on the x-axis, we're going to be looking at the number of in-context examples that we provide to the model. So these are how many f of x pairs do provide the model before the x query. And on the y-axis, we're going to look at the squared error of the prediction, normalized so that the trivial error is 1. So if my model just predicted 0, on average, it would get an error of 1. So what does an ideal algorithm look for this setting? Well, this is just something like least squares. And the error of least squares drops roughly linearly. Okay, in theory, it drops exactly linearly. as you get more and more in context examples. And the moment you get 20 examples, if the number of example matches the dimension, then the model just gets least squares, gets zero error, and the error just stays at zero. So this is ideally what we would hope to get. So this is, in some sense, a lower bound. Is the best thing you could have hoped for is the optimal estimator that estimates f given the in-context examples. Well, and it turns out the transformer is actually doing pretty good compared to this baseline. So the drop is actually also linear to some extent. The kink at d equals 20 is not exactly as sharp. Like the model doesn't exactly hit zero error, but it does improve over time. And when you reach 30 or 40 context examples, then the error is actually quite small. So this was actually quite surprising to us because it shows that we are able to train a model in a relatively natural way. And just to contextualize these are some simple baselines, things like, doing 3 nearest neighbors or just averaging out the XY products. These are simple baselines that maybe a simple model would learn, but they don't do nearly as good as the transformer does. And overall, what this shows us is that the model is actually able to learn new functions, right? So we have a function class, and the model has seen some functions from this class, but has not seen everything, but is still able to learn these functions from in-context examples. And just to emphasize, this is not something that you can explain with memorization. So even if you say, out of the linear functions that my model saw during training, even if I used the best one of these, the error would not be that low. It would be something like 0.2, quite far away from what we're getting. So in some sense, this is showing us that the model is actually able to learn these functions purely from these in-context examples and do, to some extent, correct linear regression. Now, to dig a bit deeper, maybe following a bit our theme of adversarial examples before, you can ask, what is the model learning? What is the function that the model is learning? And if you view the model as taking a prompt of inputs xi through xk, and then one query input x query, well, you can think of the prompt as being fixed, and the whole thing being a black box where you feed in x query and you get y. And you want this to be roughly f of x query. And we're comparing how well this does compared to the real function we're trying to approximate that takes in x query and then produces w transpose x query for some linear weights w. Now, one way to see how close we are is to look at the gradient of the function, the gradient of the output with respect to the input. And for the true function, well, this will just be w. And we can ask, okay, if I look at the gradient of the model of y with respect to x query, will this also be roughly w? So we can do this experiment, and we can look at a similar plot where on the x-axis, we look at the number of in-context examples that we give the model. And then on the y-axis, we're going to look at the average product, let's say at first between the gradient and w. And you see that actually, after you get 20 in-context examples, which is actually what you need to be able to fully specify, to be in the fully specified regime, then you can see that basically the gradient and the weight vector is actually aligning almost perfectly. Well, when you have fewer examples, you cannot actually recover the true weight w. But it turns out that if you project w to the set of in-context examples that you already got, which in some sense is the best you could do, then you see that this also matches really well. So this was really interesting because it shows that, okay, not only are these models working on an average input, but they're also locally correct. So this says that even in a small neighborhood around this input, the behavior is actually what you expect it to be. It actually follows the function properly. Now, the next natural question is, okay, we train on this distribution of inputs. Does the model still work when we sort of deviate from it in small ways? And what I mean by this specifically is we're going to look at some out-of-distribution prompts. And the way we can think of distributions here is that we have our model, and there are three distributions at play. So there's the distribution of x's. This is from where the space from where we sample the x. There's the distribution of functions. Even within this function class, the functions that we sample could have different weights. And then there's the distribution of the query. Where are we querying our model on? And so far, these have been exactly the same during training and testing. We fixed the distribution of x, f, and x query was coming from x. And we did the exact same evaluation during training and testing. So we did see that the model generalizes, where we didn't see if it also extrapolates to some sort of different distributions here. So let's look at a couple of examples of how we can mix things up. One very natural case is you can ask, okay, what if my inputs x are not actually coming from a univariate Gaussian, but are coming from a Gaussian with a skewed covariance? So let's say the ith eigenvalue is something like I over I squared, 1 over I squared. So in this case, the distribution of inputs is not what I saw during training. Does my model still work? Well, it turns out that it sort of does to some extent. Like the performance actually drops quite a bit. So you can see the error doesn't actually reach the great error that least squares could get towards the end. But still, up until 10 in context examples, it actually works quite well. And then, but even then, it doesn't completely go haywire, and it sort of plateaus at some reasonable approximation. Now, a sort of complementary question is, okay, what if instead of messing with the x's, I mess up with the y's? So let's say that the functions that I now look at are actually noisy functions. So I add some noise, and instead of just observing W transpose X, I add some noise to the label. And this is actually quite interesting because we see this phenomenon, which is known as double descent. And it's actually something that is quite well understood in the least squares setting, and I guess recently, that says that as I give more and more examples, if I look at the optimal noiseless estimator, which is just least squares, and I give it noisy inputs, as I give it more and more inputs, when the number of inputs that I give it approaches the number of dimensions, then I get this big spike in performance. And then things go fine again. And we see that the transformer also follows least squares and has a similar qualitative spike. So it also exhibits this notion of double descent, which gives us more confidence that, okay, it's actually doing something relatively close to linear regression. Okay, and now another test you can do is you can say, okay, what if is my model doing some variant of nearest neighbors? So what if instead of looking at the random distribution of inputs, I make sure that all the in-context examples are actually concentrated in one quadrant, one orthant, and the query point is actually in another one. And it turns out that here the transformer is actually doing really well. This doesn't seem to affect it almost at all, and is actually able to generalize in the settings. And so this shows you that you're clearly not really depending on some notion of nearest neighbor search to perform well. And one thing, like, there are a lot of interesting tidbits about how this training process works. But one thing I want to highlight is this notion of curriculum learning, where the way we train these models is we gradually increase the complexity of the function class of our training. So what this says is that, okay, if we have this function f that are W transpose X, then originally during training, we zero out some part of the X vector. So we're effectively training the model to do linear regression in fewer dimensions. So if we're training for linear regression in 20 dimensions, we start from 5, and then we train for a while with 5, and then we increase to 6, and then 7, and so on. And it turns out that this is actually pretty important. I'm going to show you here the training loss with 3 random seeds, with and without curriculum. And if you train it on 10 dimensions, these are relatively smaller problems, then both cases, both with and without curriculum, converge to a pretty low loss after a while. With curriculum, it converges faster. Now, when we go into the setting we've looked at so far with 20 dimensions, then the difference is actually much bigger. There is this, when you train without curriculum, there is this relatively long period where the loss of the model doesn't drop by too much, and then suddenly drops. Whereas if you train with curriculum, you're actually able to get pretty consistent behavior. You can see that all 3 seeds are basically overlapping. And if we're confused of why the loss goes up over training, this is that, oh, during the curriculum phase, we are making the function class harder. So every time we increase the complexity of the function class, well, the loss of the model will jump up. But if you look after the vertical dashed line, yeah, you can clearly see that by this point, the model has done really well. And this becomes even more salient if you go to 30 dimensions, whereas one of the training runs without curriculum failed. And if you go to 50 dimensions, where we're actually not able to train any models without curriculum in a meaningful way. Yeah, I don't know exactly what the optimization barriers are here, but somehow slowly warming up the model through this curriculum learning is actually having a huge impact here. Okay, so moving forward, we saw that, okay, we can train models that in context learn the class of linear functions. But what about something, and actually in a way that extrapolates, this is not just the in-distribution setting, but we saw that even when we messed with the distributions a little bit, things still work to some extent. But what about more complex function classes? And here we looked at 3 different things. Sparse linear functions. So here, your weight vector is actually 3 sparse. And here, least squares is no longer the optimal thing to do. You can use an algorithm like Lasso that actually performs better and is able to exploit sparsity and learn with fewer examples. And now, if you train the transformer to learn sparse linear functions, again, this is not the transformer that we looked at that was trained to learn linear functions. This has been trained specifically to learn sparse linear functions from here. Then it can actually approximate the performance of Lasso quite well. And again, it was not trained to perform Lasso, it was just trained to predict well on sparse linear functions. And it learned an algorithm that's actually comparable. Then we looked at something a bit more complicated, like decision trees, where you treat every coordinate of X as a feature, and then you build a random tree based on these coordinates. And this is actually a quite challenging problem, especially if you build these trees at random. And you can do things like greedy learning or XGBoost. But it turns out here that training a transformer to learn this actually does much better. We were not able to compete with the performance, no matter how much we tried. We were not able to compete with the transformer using a more classical method in this setting. And this is a setting that we don't really understand very well as a community, like understanding what are the good algorithms for learning specific families of decision trees. And I find this really exciting because it would tell us that, oh, maybe if we understand what the transformer is doing here, maybe we would be able to discover good algorithms for learning decision trees. In some sense, exactly because we're training the model to find a learning algorithm. If we could reverse engineer the final algorithm, that could be really impactful. And finally, we try training like 2-layer RL networks. So this says, okay, I'm going to sample random weights for a 2-layer RL network, and the function is actually the product of feeding X into this network. And here, a reasonable baseline is something like doing just gradient descent, learning a network of the same architecture using gradient descent. And the transformer is actually performing quite well. It's actually matching these baseline and outperforms it in certain cases. And note here that the transformer, like we're not doing any sort of gradient descent here. This is a fixed model that we just feed in these in context examples and ask for predictions about their label. Yeah. So the takeaways here are that, okay, it turns out in context learning, we can train transformers that in context learn quite involved function classes. So these are things that are not really easy, like building an algorithm that learns decision trees or learns sparse linear regression is not something that you can easily do in a simple feed-forward model. Many of these problems don't really have a closed-form solution. So in principle, in context learning can be quite real. So it's a bit hard to connect the in-context learning behavior that we see for language models in practice and say how powerful that is. But these results tell you that, well, if you train these models in the right way, then the in-context learning that you can get is actually really powerful. And actually, in a way that is not really restricted to the training distribution exactly, which gives us hope that, well, these models, you train them on some large corpus of text, and then they're able to extrapolate to some extent to other distributions and still have a relatively reliable behavior. All right, so to conclude, I wanted to, so far we looked at these two examples of really interesting behaviors of models that we didn't really expect. Both the existence of adversarial examples came as a surprise, and phenomena like in context learning came as a surprise. And we saw how basically by digging deeper into this phenomena and looking at model behavior beyond just accuracy, we can actually get a glimpse of how models can actually work. We got a sense of, oh, you know what, like models can actually rely on different features, and this is what gives rise to adversarial vulnerability. Or you know what, models can actually properly use their context to learn fundamentally new functions. And I think that this is a really promising research direction overall that says, okay, I don't want to understand just the behavior of my model on some specific downstream task, because this can mask a lot of things. But I want to try and look a bit more deeply into the various behaviors that I see. And some ways to do it is you can build bespoke benchmarks. You can build tests similar to what we did in context learning that says, okay, here's a very specific behavior I want to capture, and here's a concrete benchmark that I can actually measure this behavior with. Then, of course, the mystery of, okay, how did these behaviors actually arise? Like, as we said, like for adversarial examples are to some extent connected to the training data and what is present there, but can we build more general tools to connect how models learn and how different parts of the training data influence their behaviors we see in practice? And finally, it would be really nice if we could get a better mechanistic understanding of how these models work. Okay, we sort of, even if we understand to some extent what they're doing, understanding how they're doing it is actually important. For instance, in the decision tree examples, we saw that, oh, maybe this would allow us to discover new algorithms. Or more generally, if you're able to understand how models work, this would actually provide you with a new interface to interact with these models and change them in ways that are different from just standard fine-tuning or interacting with them and creating new capabilities by just understanding how their internals work and being able to sort of pop open the hood and mess up with things a little bit. Yeah, so that is all. I have to take any questions.
Thank you so much, Dr. Tsipras. I think this is a wonderful talk, a lot of joy I feel. This is really fundamental research, helping us understand the reliability of models and the capacity of transformers as, say, universal approximators. So let's see, I think we have time to take some questions. I see one question in the chat. So what is the structure of transformer as, say, a neural network? I think this is for the in-context learning part of the talk.
Right, that was my question. Just not familiar with transformers from before.
Yeah, so in general, these are models that are Yeah, so you take as input a sequence of vectors, and the goal is to predict the next vector in that sequence. And the way it works at the basic level is you have these alternating layers of self-attention where you mix together these vectors, you compute linear combinations of these vectors according to some similarity metrics, and then you apply per vector fully connected layers to transform these vectors individually. So the transformer as a whole is you take a sequence of vectors and then you transform these vectors applying fully connected layers. Then you do an attention operation where you replace these vectors with linear combinations, and then you keep doing this by computing other fully connected transformations and then mixing them again and so on. Yeah.
Can you hear me?
Yeah.
Okay, great. So thank you for a wonderful talk. That was really fascinating. I was just curious, to what degree do you think the existence of non-robust features in data sets is just an artifact of their size? So if you had, an arbitrary number of examples of each class, do you think all of the features would become robust at that point?
Yeah, I think that's a great question. Like, it's not entirely clear what is the answer. Like, to what extent is this is a minority phenomenon that some consistent fraction of the class has this set of examples, or whether it's a small n phenomenon that, they're sort of individual samples. I do have a feeling that there are things that would persist. There are definitely patterns that seem real, and again, building again on a lot of this other work on things like high frequency components, I feel these things wouldn't necessarily go away as we get more and more data. But I do have a feeling that a lot of the other weirdnesses that we see would potentially go away. And I feel that this is one of the places where training on more data is one of the ways that you can sort of get wins on this robustness accuracy trade-off. So yeah, basically it should be possible to, because if you think about one way to view this phenomenon is that, okay, maybe for our current dataset sizes, robust features alone are not sufficient to actually get really good accuracy. So the fact that we have non-robust features, you can think of them as a crutch that models rely on. But if you really had a lot of data and the model and the robust features were actually clearly salient, and we had enough data to learn the models that don't really rely on this, well, maybe then you would be able to get robust models for free to some extent. But yeah, I think this is a really interesting question that I have thoughts, but I don't really have a crisp understanding.
Hi, thank you for the wonderful talk. So specifically for the first part, which is with robustness, where you try to add the inner objective of maximizing the perturbation as the worst case. Can this be thought of as something like data augmentation, and is it something that we can leverage for other training? So instead of right now, data augmentation has a lot of the affine transformations, but if we can adding the worst case perturbation be something like of an additional data augmentation for improving performance of other tasks?
Mm-hmm. Yeah, I guess is this data augmentation? I guess the answer is yes and no. I guess conceptually, yes, it is data augmentation because you're training on different versions of your data. I think it's also quite different in the sense that you're not training on a random transformation, but you're training specifically on the worst case transformation. And this has a different effect. For instance, we know that if you just train on random noise, then you don't get robust models. If you train by adding random noise of the same magnitude as your perturbations, then you don't really become robust. So there is a difference between average case augmentation and worst case augmentation that I think we don't fully understand well yet. When should you prefer one to the other? But I definitely feel that this is a very useful primitive. We have seen plenty of evidence that training models to be robust to a worst case L2 perturbations causes them to have different behavior. For instance, there are these results that show that if you train models to be adversarially robust, then they can actually transfer better sometimes to downstream tasks. So I feel that this is a very powerful tool that we have in our toolkit that says, here is a way that I can change what my model relies on. And sometimes this change is useful, and sometimes it might be not, and we'll just drop accuracy, but yeah, it definitely could be applied to other settings. And it actually is something that even if you really don't care about the robustness of your model from a security perspective, there is merit in thinking about it, actually training on worst case transformations.
Oh, thank you for a great talk. I have a couple of questions. Can you elaborate a bit about this XGBoost comparison? Because it's not clear to me like what function it was trying to approximate and why it's not lower bounded by XGBoost performance.
Yeah, so in general, like, yeah, so just to clarify about the specific structure here, maybe I can quickly go back. Yeah, so here the structure is we have x's in 20 dimensions, and then you build the decision tree of depth 4 by randomly picking a random coordinate, then looking at the sign and branching based on the sign. So you pick a random coordinate. If it's positive, the left subtree goes one way, the right subtree goes another way. And the way it works is basically, yeah, I sample one of these random subtrees, and then I generate data according to that tree.
I see.
And this is in fact a really challenging setting because XGBoost, what a greedy algorithm is trying to do says, okay, I'm going to try to find a variable to split so that I minimize the variance of my two subtrees. But the problem is that because there's so much noise here, and we're working with x's that are sampled from random Gaussians, it's really hard to tell apart the two subtrees at the root. So it's very likely that you're gonna split the wrong way. So greedy just doesn't really work, at least up to 100 examples. And XGBoost is doing similar things. Like, yeah, like in some sense, if you have a real world application where there is a real feature like, oh, age is predictive of something, then you would expect these algorithms to find this feature because there's actually a pretty salient reliance from this feature to the output. But here, because there's so much noise, it's actually really hard to distinguish these things.
So basically the task is approximating piecewise, like random piecewise linear function, right? And XGBoost like.
Yes, exactly. Yeah, piecewise constant.
Sorry, piecewise constant. Yeah, piecewise constant function, and XGBoost just kind of does it worse than transformer. What about inference time? So like not inference, training times. Like how long does it take to train the experiments compared to XGBoost?
Oh, it's not even comparable. Like XGBoost you can run in like seconds. These transformers take like a day to train. I mean, the inference is quick. Again, the inference is seconds. So it's still like, okay, yeah, even inference on these transformers, we should probably figure out the exact times, but I think it's definitely comparable. The argument here is, I would be hard pressed to formulate an argument that says you should be using transformers over XGBoost. This is because, again, this is like sort of a weird case, and perhaps this is not ready yet to be something that you would try to apply. It's more about showing that, well, it turns out that you can really discover non-trivial algorithms that would do better than bespoke baselines we have.
And final short questions, like have you tried to like fine-tune, I don't know, some existing large transformer model to this task and to get like better training time compared to training transformer from scratch? Because if you want to generalize across tasks, maybe it might like be faster.
Yeah, so I think that, yeah, both directions are interesting. So I guess the question of like, if I pre-train on text and then I train on these tasks, what is the impact? But also, what if I pre-train on these tasks and then train on text? Is this something that I'm going to get a boost on? Let's say, if I train on models on these tasks in context learn linear functions, will my model discover good primitives for learning text? And we haven't done either of these directions. I think both of them are interesting, and I would be curious if you try and you see something.
Thank you.
Any other questions? If not, let's give Dr. Tsipras another round of applause and thank you.
Thank you so much.